In the previous class, I introduced the notion of a proper cone, and we were studying properties of proper cones and generalized inequalities that are derived from proper cones. So recall that a cone is said to be proper if it is convex, closed, solid, and pointed. We saw a number of examples of proper cones. And the examples to always keep in mind are the non-negative orthant in Rn, the set of all PSD matrices, and norm cones. Right? So all of these are examples of proper cones, but you can construct many other examples as well. So in the last class, we proved that the set of PSD matrices is a solid cone and hence proper. But what was most interesting for us was this notion of a generalized inequality that is derived for proper cones. And so basically we say that if K is a proper cone, then the generalized inequality says that X is less than or equal to Y if Y minus X lies inside the cone. Okay? And the most common example of a generalized inequality, one that you already seen earlier, is that of the component-wise inequality. So given two vectors, the one is component-wise greater than or equal to the other, then we say that one vector is greater than or equal to the other. And we saw that if K is a proper cone, then the generalized inequality so defined induces a partial ordering. So it satisfies these properties of being reflexive, antisymmetric, and transitive, similar to your standard notion of inequality of real numbers. But what is different from the inequality for real numbers is that not every two vectors could be comparable. Right? For a given generalized inequality, it's possible that some vectors cannot be compared with respect to each other. But if two vectors can be compared, if one is greater than or equal to the other, then this greater than or equal to satisfies some natural properties. We also saw some more properties of generalized inequalities. So for example, if you take a translate of two vectors, one which is greater than or equal to the other, if you shift them, then they're still greater than the still inequality still holds. And scaling up two vectors by the same amount does not change the inequality. And it's also true that these generalized inequalities are also preserved under limits. So if you have two sequences and each element of and the ith element of one sequence is less than or equal to the ith element of the other sequence, then the limit of the first sequence is also less than or equal to the limit of the second sequence. And using this, we could, since we have an inequality, we have this notion of a minimal element. If it's possible, we can also define a minimum. So given a particular set, we say that a vector is the minimum of that particular set if this vector x star is less than or equal to every element in that particular set. This is of course assuming that you can compare this vector with every element in that particular set. Right? It's possible that not every pair of elements in that set is comparable. But as long as you can compare this vector, the minimum vector, with every other element, then the minimum exists. But nevertheless, given any set, you can always define a minimal element. Right? So we say that a vector is a minimal element if x is less than or equal to y. If the only way you can get x less than or equal to y is if y is equal to x. Okay. So again, we saw a few examples for the component-wise inequality, and in particular for when the generalized inequality is the component-wise inequality, the set of all minimal elements are sometimes called the Pareto-optimal points. So the idea of minimal elements, particularly in multi-objective optimization problems, essentially occurs in the following setup. So suppose I have some f. Suppose I have two objective functions, f1 of x and f2 of x, and my goal is to somehow try to minimize both f1 of x and f2 of x. So the goal, so x belongs to some set, and the goal is to minimize both f1 of x and f2 of x. All right, so for example, this x could be a vector in R2. It's possible that x is equal to some x1 comma x2. So this is my set S, and corresponding to every vector x, I can also compute f1 of x and f2 of x. All right, so every point here, let's say I take some x1 comma x2, this corresponds to some f1 of x1 x2 and f2 of x1 x2. So this is mapped to some point in this two-dimensional plane. Right, and I can consider the image of this particular set under f1 and f2. So every point here maps to some point over here, and I get, so this is basically the image of S. Right. So if I want to minimize both f1 and f2, effectively that just corresponds to finding the set of all minimal points of the image of S. So the goal basically reduces to find set of all minimal points of the image of S under the component-wise inequality. Yes, every minimum point is minimal. Right?
So if minimum exists, then a set of minimal points is similar.
Yes, exactly. Okay. So that's not, so if x is the minimum, then certainly yeah, sure. So if x star is a minimum, then certainly the set of all minimal points is just considered is a singleton set. But in general, the minimum may not exist. In fact, is it possible? Is it necessary that a minimal element should exist? Can you give an example where a minimal element does not exist?
Variable points are equal.
Okay.
Because find one less than equal to the other.
But can you have 2 points which are both less than or equal to each other? If you have a generalized inequality, you can't, right? Because it is antisymmetric. Yeah? Okay. So, what is the example? What is the region? Just this set. Okay. There are no minimal points, or in general, suppose I take any convex polygon.
When it's points, points which form the, I can say that they don't.
Why not? So you will be able to find a point which is minimal, right? If I take a polygon, so for example, this set of points would certainly be a set of minimal points. Correct. I'm assuming again you have to define the generalized inequality, but I'm assuming let's just take the component-wise inequality. Okay. So let's take Rn, right, under the component-wise inequality. What is the set of minimal points? Right. So there is no set of minimal points. So this is an example. If it's loosely speaking not bounded from below, then this will not have a minimal point. For example, you just take R, right? What is the minimum of all elements in R? There is no minimum, right? You define the minimum to be minus infinity, but minus infinity is not a real number. So this is an example of a set which does not have a minimum. And similarly, you can define a set which does not have any minimal point. But on the other hand, if you take any bounded set in Rn, this will always have at least one minimal point. In which I'm assuming that this extends to infinity. Oh, it is just 2 line segments. What about this particular point? So, okay. Which one? Okay. That's okay, right? So, in other words, so is this point less than or equal to this point? Yes, it is, right? It's less than or equal to this point. Similarly, okay, so every point, so this, let me draw this separately, and also look at this in a more analytical fashion. So how do you define this set? Let us say it is a set of all x, which can be written as, suppose I fix, let's say alpha comma 1, or let's say 0. Alpha 0, or say 0 alpha, for alpha varying between say -1 and 0. Okay, so basically this goes from -1 comma 0 to 0 comma 0, and similarly along the y-axis or the vertical axis, it goes from 0 comma 0 to 0 comma -1. Okay, so let's think about this visually. First, you'll agree with me that this point is less than or equal to every point along this particular line, correct? Because this is the set of all alpha commas, this is the set of all alpha comma 0. So alpha varies between -1 and 0. So -1 comma 0 is less than or equal to every point over here. But can you compare this point with any point here? You can't, right? Which is fine. Okay. Among the set of all points that you can compare this to, this should be a minimum point. Then it's a minimal point. So loosely speaking, one way of thinking about a minimal point is that, so x is a minimal point if you look at all points that you can compare x with, then within that set this should be the minimum. So this is in fact a minimal point, and similarly this is also a minimal point. Then all the points are minimal. Yes. So for example, let's consider a line that looks something like this, that makes an angle of makes an obtuse angle with respect to the horizontal axis, right? Can you compare any two points with each other? You can't. Just think about it a little. I mean, in fact, you can try to define this more formally, just as I had done over here. You'll see that no two points in this particular set along this line can be compared with respect to each other. So it turns out that all of these points are minimal points. Okay, is that clear? Any questions?
With three or more variables, you have taken the partial differentiation and equated it to zero. Like first partial differentiation with x, y, z is the variables in the equation. And taken the partial differentiation with respect to x or y or z.
But there's no notion of, these are not functions, right? These are sets.
Like line, right? It can be think along the line, you can play with the partial function and you can equate it to zero, and that stage you're getting a minimum.
Not really. So here every point is minimal, right? That's the point I'm trying to make. And ultimately all of this depends on what is your generalized inequality, what is the proper cone with respect to which you're defining your generalized inequality. So these points are all minimal, assuming that you have the component-wise inequality. Right? If I choose a different generalized inequality, maybe with respect to the say the norm cone, the two norm cone, right? These may not be the set of these. All of these points need not be minimal. So ultimately, all of these would ultimately depend on how we are defining your generalized inequality. So in each case, you will have to check whether a given point is minimal or not. Right? In fact, the non-negative orthant is one example of a proper cone. But I can also consider the non-positive orthant, right? The set of all vectors for which all the components are less than or equal to 0. Right? So in 2D that would correspond to the third quadrant. Right? So in that case, these 2 points would not be minimal. What would be the minimal point or set of minimal points here? Yeah? Yeah, so there will be only one minimal point, and that would be 0, 0. Which one?
It's a third quadrant.
Correct.
So,
Yes.
zero is greater than every point.
So you have to be a little careful over there, right? So suppose I define my cone to be the set of all vectors x in Rn such that xi is less than or equal to 0 for all I. Okay. So when do you say that a vector x is great with respect to this generalized inequality? When do you say that vector x is greater than or equal to, or since we always define less than or equal to with respect to k, when do you say that this is less than or equal to y? When y minus x, again we just use the definition, when y minus x is in k, right? But when is y minus x in k? When all elements of y minus x are less than or equal to 0. Right? When this less than or equal to is defined for real numbers. It's a standard inequality for real numbers. So yi minus xi should be less than or equal to 0. Correct? So what does that mean? It means that yi is less than or equal to xi. Correct? But here y is greater than or equal to x according to a generalized inequality. So it feels counterintuitive, but that's why you have to be careful when defining your proper cone. So these are two different proper cones, but inequality with respect to one cone could be very different from the inequality with respect to the other cone. In this case, this is also a component-wise inequality, but here component-wise less than or equal to, this is not component-wise less than or equal to, it's component-wise greater than or equal. Okay. So the set of all minimal points with respect to one cone could be the set of all maximal points with respect to another cone. Okay, it may seem a little bit confusing, but that's why we have to stick to what the definition is. In which case, you mean to say with respect to the second cone for this particular set? So in that case, basically the minimal points and maximal points get flipped, right? So with respect to the standard non-negative orthant, these two would be the set of minimal points, and this point would be maximal. But if I take my cone to be the third quadrant, then this yellow point would be the minimal point. It would be a minimum, in fact, and these two would be set of maximal points. Okay. Any other questions? Okay. Yes. Yes. I think I'd given that as an exercise. So what would be the set of minimal points? Correct. So that would effectively be along the boundary. It would be basically from here to here, right? These would be the set of all minimal points. All right, assuming that it's a component-wise inequality. The cone is the first quadrant, right? So these would be okay.
Disjoint sets of
I'm sorry.
disjoint sets of here
Mhm.
middle points are always continuous.
Okay.
Is it possible to have disjoint intervals
So,
in which I have
something like this. Here you have,
but in a continuous, it's sort of a discontinuous.
okay,
Like in a closed polynomial or something along those.
okay.
Is it possible to have disjoint?
in general, I mean, you could always construct weird examples like, for example, like this, right? So this, you take a set that looks something like this, all right? Um, you can see that this would be a minimal point and this would be a minimal point, but nothing else in general. But on the other hand, if you constructed a convex polygon, then the set of minimal points would either be unique, there would be a unique minimum, or all you would get a continuous set. Okay. Okay. So again, going back to our problem, suppose I have a multi-objective optimization problem wherein I have two functions f1 and f2 that I want to simultaneously minimize. Then that effectively boils down to finding the set of all minimal points of the image of, of the constraint set under the two functions f1 and f2. Okay. And this is of course under the component wise inequality, and this set of minimal points has a special name. It is called the set of all Pareto optimal points. Okay, and it's specially under the component wise inequality. So in this case, the set of all minimal points would look something like this. Sure, you could also define with respect to maximal, but think about it, maximal with respect to one cone would just be minimal with respect to another. So basically you take k, the set of all minimal points with respect to k would be the set of all maximal points with respect to minus k. Okay, any other questions? All right. So again, we're defining a number of these objects on sets. Right. So just as we've defined cones, we'll also define what are called dual cones. And in maybe the next couple of classes, we'll see why this notion of duality plays an important role. So given a particular cone, I'll define a dual cone in the following manner. So given a cone K, the dual cone so K star is defined as the set of all vectors such that the inner product of this vector with every vector in K is greater than or equal to 0. So a vector x lies in the dual cone if and only if the dot product of x with every vector in K is always greater than or equal to 0. So firstly, is this a cone? Yeah, it should be a cone because if if the dot product of x with every vector y in K is greater than or equal to 0, then what can you say about alpha times x? So if x is in K star, then dot product of x with every vector in K is greater than or equal to 0. But that also implies that the dot product of alpha times x with y is greater than or equal to 0 for all y in K and for all alpha greater than or equal to 0. Right, so alpha x belongs to K star for all alpha greater than or equal to 0. So K star is in fact a cone. What more can you say about K star? Is K star a convex cone? Yeah, it should be a convex cone because in fact if x1 and x2 both belong to K star, then every conic combination should also belong to K star. Again, this just follows from the linearity property of the inner product. So if x1, x2 lie in K star and you take any theta 1, theta 2 greater than or equal to 0, then the inner product between theta 1 x1 plus theta 2 x2 with any vector y, this is simply theta 1 times the inner product between x1 y1, sorry, x1 y plus theta 2 times the inner product between x2 and y, and this is greater than or equal to 0 because each of these two is greater than or equal to 0. Right? So let's look at another property. Suppose that I have two cones, K1 and K2, such that K1 is perhaps a subset of K2. Okay. What can I say about K1 star and K2 star? Is it possible to say something about K1 star and K2 star? Is one contained in the other? K1 star is a subset of K2 star. Are you sure? So let's consider an element of K2 star. Okay. So consider any vector x that lies in K2 star. So I know that K1 is a subset of K2, right? So the inner product of x with every element y is greater than or equal to 0 for all y in K2, but also in K1, right? Because after all, K1 is a subset of K2. So if if this holds for every y in K2, then it definitely has to hold for every element in K1. Okay. So what does this mean? If x lies in K2 and this happens, then x should lie in K1 star. Correct? So now what can you conclude about the inclusion? Every vector in K2 star lies in K1 star. So K2 star is in fact a subset of K1 star. Okay, so let's see some examples to see why this is the case. Right, so let's start with our favorite cone, which is the first quadrant. Okay, so let's assume that K1 is the non-negative ortho. So set of all x such that xi is greater than or equal to 0 for all I. Okay, and let's assume that K2 is, or maybe I should call this K2. So now let me take a cone, or let me just take this. I'll take different cones. Suppose that this is my K1. K2 is, let's say, the half space. Okay, the half space of all vectors. So the set of all x such that yeah, so maybe 1 transpose x, or since we're looking at R2, say x1 plus x2 is greater than or equal to 0. Okay, so what set does this correspond to? Geometrically, what does this set look like? Yeah, so you basically everything to the right of this particular line, right? So this is K2. This is my K1, and I'll also define K3 as maybe just the ray just shooting out of the origin. Okay, I can take any ray. So let me say x equal to alpha times 1 comma 1, alpha greater than or equal to 0. This is basically the 45-degree ray. Correct. For each of these, let us try to compute the dual cone. So clearly I have K2 contains K1 and K1 contains K3. Okay. Now let's try to see what the dual cones are. Well, first let's start with K1. What is the dual cone of K1? Any guesses? So remember, the dual cone of a particular cone is the set of all vectors which have positive inner product with every element of this particular cone. Right? So first let's try to guess. Okay, can a vector in the dual cone have a negative component? Can it have a negative component? Again, we're looking at k1, right? Suppose that a vector x has one negative component. Okay, can you ensure that the inner product with every vector in k is greater than or equal to 0? Yes. So let's look at k1. K1 is the set of all x such that xi is greater than or equal to 0 for all I. So we want to guess the dual cone. So suppose, so you consider any vector y where some yj is strictly less than 0. Okay. For the vector y to belong to the dual cone, the inner product with every vector in k1 should be greater than or equal to 0. But if even one component of y is less than 0, can you ensure a positive inner product with every vector in x? You can't, right? Because I can simply consider the following vector, which is all zeros except a 1 in the ith component, right? So the jth component. And the inner product of this vector with the vector y will be strictly less than 0. So yj, so y cannot belong to k star. Okay, so that's something that we've established. Now suppose that all the so obviously if any component is less than 0, then y cannot be in the dual cone. But what happens if all the components of y are greater than or equal to 0? Then the inner product with every vector in k1 will also be greater than or equal to 0, because you are just taking a sum of non-negative numbers, right? So any y that belongs to k1 also lies in k1 star. So every vector in k1 is also a vector of k1 star, and every vector outside k1, that is, even if one component is less than 0, then it cannot lie in k1 star. So this is an example where k1, the cone, is also equal to its dual. So this is an example of what is called a self-dual cone. Okay, any questions? So let's try to interpret this statement geometrically, right? Suppose I give you a particular vector, okay, in say R2, right? I'll just take R2, pick a vector of your choice, maybe some vector here. So this is a vector v. Okay, what is the set of all vectors in R2 which have non-negative inner product with v? Yeah, correct, but something more. What does it look like? it's basically the half space with v as the normal vector, right? So it should contain the vector v. It's a half space passing through the origin and having v as the normal vector. So this would basically be this would be the set of all vectors which have non-negative inner product with v. Okay. Now think of a more general cone, right? So suppose I have, let's try to extend this intuition to a more general cone. So in general, in R2, what would a cone look like? You could think of it as having sort of two rays, right? And the entire region between these two rays. That's an example of a cone. Suppose this is my cone K. Okay. So let's think about this a little bit. Let's take the two extreme rays. Okay. I'll try to find the half space of all vectors which have non-negative inner product with this particular ray, and the half space of all vectors having non-negative inner product with this particular ray. What would that look like? So I'd get, so basically everything above the green line is the set of all vectors which have non-negative inner product with every vector in this. Okay. And similarly, I can do the same for this particular vector. Let me draw that in, say, yellow. So everything to the right of the yellow line have basically positive or non-negative inner product with this particular ray. All right. So what do you think would be the dual cone? Remember, it is a set of all vectors for which you have positive inner product with every element within this particular cone. Right. So it would be the intersection of these two half spaces. Correct. So everything to the right of the yellow line has non-negative inner product with this line, and everything above the green line has non-negative inner product with this. So if you want to ensure that you have a non-negative inner product with every vector in between, then essentially it would be the set of all vectors to the right of the yellow line and also above the green line. Correct. So in this case, the dual cone would basically be this entire region. Right? It doesn't include the region between these two lines. Okay. So you can imagine so this is basically one example of a cone, right? It's a convex cone, and suppose that the angle between these rays is equal to theta, right? As I increase, suppose this is theta, the dual cone also looks similar, but with a different angle, right? Let's call that theta prime. This is my theta prime. So as I increase theta, what happens to theta prime? It decreases, right? You keep increasing. So if theta is very close, so if theta is exactly equal to 0, then the original cone K just corresponds to a single ray. In which case, what is the dual cone? It's an entire half space, right? So theta prime would be equal to 180 degrees. But as I increase theta, theta prime decreases. Now similarly, when I let theta to be equal to 180 degrees, what happens to theta prime? That becomes, that's equal to 0, right? That becomes a single ray, right? So again, this is intuitive, right? We still need to prove that. So let's go back to the 3 cones that we had. Okay. So K2 was basically the set of all x such that x1 plus x2 is greater than or equal to 0. So now what is K2 star? What is the dual cone of K2? It's actually equal to K3, right? So firstly, observe that every vector in K3 lies in the dual cone of K2. So basically any vector alpha comma alpha for alpha greater than or equal to 0, the inner product with every element in K2 is greater than or equal to 0. Actually that follows just by definition over here, right? Since x1 plus x2 is greater than or equal to 0, alpha x1 plus alpha x2 is greater than or equal to 0 for all alpha greater than or equal to 0, right? So, but we also need to show that any element that does not lie in K3 also does not lie in K2 star. Okay, so you just consider any alpha comma beta where beta is not equal to alpha, right? Is it possible to construct a vector here such that the inner product is not greater than or equal to 0? For x such that x1 plus x2 is greater than or equal to 0. So we've established that every alpha in R lies in K2 star. So let us consider alpha, any vector alpha comma beta, it should be R greater than or equal to 0. So consider any vector alpha beta for which alpha is not equal to beta. Okay, can I find a vector in K2 which has, let's say, strictly negative inner product with alpha comma beta? Okay, can you give me an example? Sorry? For a fixed alpha beta, I give you some alpha comma beta. Let's assume that both alpha and beta are greater than or equal to 0 for simplicity. Okay, but alpha is not equal to beta. Can you find a vector in K2 which has negative inner product with alpha comma beta? Uh, 1 comma minus 1, are you sure that will always work? You're close, right? One comma minus 1 belongs to K2, yes. Correct. So again, I want something that's general, right? For any alpha beta.
So we can save that line.
Correct. But you're close. So 1 comma minus 1 may not work for all possible alpha comma beta. But then you can consider either 1 comma minus 1 or minus 1 comma 1. Right? So if alpha is not equal to beta, then for sure if alpha is not equal to beta, then either alpha minus beta is less than 0 or beta minus alpha is less than 0. Correct? One of these two must happen. So in this case, I can just consider 1 comma minus 1, and in this case I can simply consider minus 1 comma 1. Both these vectors lie in K2, right? And this just works. So such an alpha comma beta would not belong to K2 star.
Sir, if x1 plus x2 greater than should have that we have x1 plus x2 greater than
I'm sorry?
if we have x1 plus x2 strictly greater
If I have x1 plus x2 strictly greater than 0, okay, still fine.
than these two sets.
Um, so, okay, it's a good question. So let's consider that separately. So consider K2 prime, or let me call this K2 bar, which is the set of all x1, x2 such that x1 plus x2 you're saying is strictly greater than 0. Will this be a cone? Are you sure? Does it contain the 0 vector? It doesn't, right? So it should definitely contain the 0 vector. So is there a way of making this a cone? Just take the union or x1 equal to x2 equal to 0. Okay, so this forms a cone. It's not a closed cone, but it's a cone. So let's see what K2 bar star equals. My claim is that this is also equal to K3. And why is that the case? Well, again, it's the same argument. If alpha is not equal to beta, then either alpha minus beta is less than 0 or beta minus alpha is less than 0. Okay. Now I can't choose 1 comma minus 1 or minus 1 comma 1. But I can always perturb this by a little bit and still guarantee that the sum is strictly greater than 0. And at the same time this is satisfied. So if alpha minus beta is less than 0, then let's say alpha minus beta equals some minus epsilon, or beta minus alpha is whatever, it's less than minus epsilon or it's less than minus epsilon. I can always find an epsilon such that this happens, right? Then in that case, all I need to do is just consider 1 comma maybe minus 1 times minus epsilon. Let's see, alpha minus beta. So maybe I need to be a little more careful. Beta. Effectively, all I need to show is that some slight perturbation of this will still result in a strictly negative inner product, right? So basically all I need to do is just consider 1 comma minus 1 plus delta or minus 1 plus delta comma 1, and I'll always be able to choose a delta such that the inner product with this is strictly less than 0. Okay, so the inner product with this, suppose that this is less than minus epsilon, then the inner product would be alpha minus beta plus beta times delta, right? I know that this quantity is less than minus epsilon, so all I need to do is choose a delta such that this quantity is at most, let's say, epsilon by 2. Then the inner product would still be strictly negative. And I can always choose a delta such that that happens. So in fact, K2, even if you choose this, consider this particular cone, the dual cone is still K3. Correct.
So we need to make sure that this point lies on the set K2.
Correct. But that is true, right? What is the sum of these two? These two entries. So x1 plus x2 is 1 plus minus 1 plus delta. It's delta. So as long as delta is greater than 0, it lies in K2 bar. Correct? You can fill in the details later. Okay, so going back, so the dual cone of K2 is equal to K3, and the dual cone of K3 is equal to K2. Okay, so going back here, we've seen that K1 star equal to K1, K2 star equal to K3, and K3 star equal to K2. And now what is the chain of containment? We have K2. Let's look at K2 star. K2 star is K3, that is contained within K1 star, which is contained within K3 star. Okay. So in this particular example, what is the dual of K2? Turned out to be K3. What is the dual of K2? It's K2 itself, right? Again, take K3. What is the dual of K3? K2. What is the dual of it's again itself, right? Similarly, take K1. What is the dual of K1? K1 itself. But is this true for all cones? We just saw an example, right? Let's look at this K2 bar. What is the dual of K2 bar? It's K3, right? But what is the dual of K3? It's equal to K2, which is not K2 bar. Correct? So in general, the dual of the cone is not necessarily equal to itself. Okay? Yeah, it has to be closed, but also it has to be, it requires one more property. Can you guess what that property might be? Convex, right? Because the dual of a cone is always a convex cone, right? Even if the original cone is not convex, right? So if you look at the dual of a particular cone, this will always be equal to the closure of the convex hull of K. So if K is both closed and convex, then the dual of the dual is the cone itself. So that's a useful property. Another property is that if K is a proper cone, then the dual cone is also proper. For something to be self-dual, I'm not sure if I can give general conditions. So here are some examples for you to consider. Okay, so try to find the dual in each of these cases. Right? So K is a subspace. Okay. So K being equal to some ray. That's something we've already seen. And again, half space. Something slightly more complex. Say the second order cone. And the set of PSD matrices. Try to work out each of these cases. In general, there's no way of computing the dual cone. Right? You first make a guess and then prove that that's in fact the dual cone. And at least in all of these cases, you will be able to guess what it is. Okay. So for a subspace, what would you guess the dual cone to be? Yeah. A point in general. Any subspace. Okay. Any other guesses? Okay, I claim that the dual of a subspace will be some other subspace, but I leave you to think about it's going to be the dual subspace. Right? For a ray, the dual is a half space, and for a half space, the dual is a ray. When I say half space, it always passes through the origin. Second order cone is something I leave you to think about. Okay. For the set of PSD matrices, any guesses? Yeah, you'll see that the set of PSD matrices itself is the dual cone. But you'll have to prove each of these, which takes a little bit of effort. Okay. Any questions? Okay, so let's have a quiz. Right.